Good afternoon, everybody. We will begin in just a few moments. We're going to give people a few minutes to enter the webinar. So we'll get started here in about one or 2 minutes. Before we begin, just a few housekeeping items. When you entered the webinar, all lines were placed on mute to prevent any background noise. This presentation will last about 40 to 45 minutes, after which there will be time for a Q&A. At any time, you can type your question into the Q&A box, and we will address it at the end of the webinar. If you are experiencing technical difficulties, you can use the chat feature to send me a message, and I will help you get through that technical difficulty. We will unmute lines. If anyone wants to ask their question directly to Lauren at the end of the presentation, you can use the raise your hand icon at the top of your screen, and I will unmute your microphone in the order that your question came in. So with that, Lauren, it's 3:01. If you want to wait another 30 seconds, it does look like there's people still entering the webinar. This webinar is being recorded, so for people who do join late, you can go back and listen to it. The webinar link will be sent out to everyone who registered at the conclusion of the event. So Lauren, I will pass this over to you.
Okay, thank you, Maria, and good afternoon, good morning, everyone. Thank you for joining us today. My name is Lauren Loudon, and I am the OEM Business Development Manager at LabSphere. And so today is the first part of a webinar series we are hosting that covers fundamentals and applications of diffuse reflectance materials. The specific topic for today is what makes a good diffuse reflectance material and why does it matter? And there will be a follow-up. We will host another webinar in February, specifically on laser cavities and laser power measurement. And then we will have another webinar in March focusing on spectroscopy applications related to diffuse reflectance materials. I will touch on those briefly today, but only kind of at a superficial level. And so for those of you that don't know, back in April of 2024, LabSphere and International Light Technologies merged together. And so we are now one company with two separate brands. And what's nice about this is it brings two authoritative brands in radiometry and photometry together to work with you and to help enable your product's success. And at LabSphere, we've always said measure any light source, create any spectrum, or reflect any wavelength. And those are the three verticals that LabSphere works in, and International Light Technologies really fits nicely into those verticals. So jumping right into the topic for today, we'll start with what makes a good diffuse reflectance material. And, at the first thing I have on the list is that diffuse reflectance material be durable. So certainly there are matte papers and other materials out there that exhibit a pretty nice near Lambertian diffuse reflectance over a particular spectral range, but those materials are not durable, and so the applications that they can be used in are quite limited. So I always like to put durability at the top of that list, especially when we get into analytical equipment or LiDAR targets, things like that, where we really need a durable material in order to enable testing and instrumentation development. The second thing on the list is that material have a spectrally flat reflectance, okay? And this is important because we really want to be able to assess across a wavelength range. Certainly some applications only require one wavelength range, but we do want a spectrally flat surface, especially if we are working in the broadband regions. And then of course, a good diffuse reflectance material needs to exhibit um, near Lambertian characteristics, right? So if we had a Lambertian surface and we looked at the BRDF, we would have a 1 over pi value at all angles. And this is kind of showing a diffuse reflectance surface here where you're getting hemispherical reflection. I will go into this in more detail. I'm not going to talk about BRDF today. And the bad and good on this image are really referencing using near Lambertian surfaces for calibration targets, right? So you don't want a specular surface if you're doing some form of calibration, unless your application specifically required that. So to start off the talk, I like to start with reviewing the radiometric and photometric quantity of intensity. And intensity is one of the most misused word in radiometry and photometry. I misuse it sometimes. It's part of our vernacular. And so it's easy to say intensity when we actually mean radiance or irradiance or flux. And so intensity is defined as the flux per unit solid angle in a given direction, right? And so we have some power propagating through a solid angle. I'm trying to represent that here. Radiant intensity is defined as watts per steradian, and luminous intensity is lumens per steradian, and lumens per steradian is equal to the candela. So when defining intensity, we do assume a point source. And if we wanted to, we don't measure intensity, but we can obtain intensity from a radiance measurement if we measure radiance, if we integrate over the area. And I will touch on radiance in a few more slides. So the type of reflectance that most people are familiar with, probably not the audience here because you're in a talk about diffuse reflectance, but most people in general are really, we intuitively understand specular reflectance because of mirrors. And, specular reflectance occurs when light reflects off of a smooth polished surface like a mirror. And with specular reflectance, the angle of incidence is equal to the angle of reflectance. Okay, and light is typically reflecting in a predictable direction, and the intensity of that light, the light being reflected, if it was a perfect surface that didn't absorb any light or anything like that, it would be equal to the reflected beam would be equal to the incident beam, but that's not the case in real life. So we have to adjust the reflectant intensity based on the material's reflectance factor at the given wavelength of interest, and also the angular component. And so really, when we're thinking about diffuse reflectance, we want the opposite of specular. And so that kind of brings us to Lambertian surfaces. And so the easiest way to think of a Lambertian surface is that light reflects off of a surface in a hemispherical nature, right? And that material is isotropic across its surface. What's really taking place is that the intensity of the reflected light off of the surface is proportional to the cosine of the angle relative to normal, right? So here's our normal. The intensity is relative to the incident angle. Okay. And what we see is that because intensity at some given wavelength, or sorry, some given angle of theta is proportional to the cosine of theta, we get this, the intensity at that angle is equal to the intensity naught or normal times the cosine of theta. And if we were to look at that in a polar plot, what we see is that the intensity is greatest at the 0 degree, cosine of 0. And as we approach 90 degrees, we approach 0 and the intensity drops off. So what's interesting about a perfectly Lambertian surface is that in theory, it would exhibit constant radiance from the varying observation angles, which in some ways seems to be counterintuitive given that intensity approaches 0 as you approach 90 degrees. But now we can think about what radiance is, and radiance or luminance, if we're working in photometric units, is the power per unit solid angle per area. Okay, and that's represented here. Um, the and I'm showing this as an integrating sphere. There's other ways to demonstrate radiance, obviously, but I think it's easy to think of the area of an exit port that we could calculate the area of, and then we can, we know the solid angle that the light is exiting through. Now, it doesn't really matter where we evaluate the beam. We can calculate radiance at any point along this beam, and it's going to be the same. The units for radiance are watts per meter squared steradian, if we are in radiometric units, and if we're working in photometric units in luminance, we would think of lumens per meter squared steradian, which is equal to the candela per meter squared. And so what's nice about this, and what I kind of like about the photometric unit when we're thinking about radiance, is candela is intensity, right? So radiance is equal to intensity divided by the area. And I, I, I just really like how the photometric unit shows that. And so now, if we just think about observing a um, a circle. So if I just held out a circle that was within my field of view, um, we're not talking about an infinite plane here or anything like that. If I just held out a circle in front of me, and when I'm at normal incidence, I see the perfect circle, area is the greatest. Now, as I rotate that, if I was to take that circle and rotate it through space, I start to see an ellipse. And what's happening is in that observational case, the ellipse actually has an area that is falling off proportional to the cosine of theta. Okay, so we end up with, we have Lambert's cosine law, which states that the intensity of light at some angle of theta is equal to the intensity, the normal intensity, or the intensity of light at a normal incidence times the cosine of theta. And what we see with area is that area also follows that same cosine of theta law. It's proportional to cosine of theta. So if I had that circle in front of me at 90 degrees and at 0 degrees and I rotate it all the way, eventually I'm just staring at the side of something and I no longer observe the area. And so what's nice about that is, we can state that quite simply down here. We have that the radiance at some angle of theta is, equal to the intensity at that angle divided by the area at that angle. We can break that out to look like the intensity at the normal times the cosine of theta divided by the area at normal times the cosine of theta. Cosines cancel out, and what we see is that the intensity at the normal divided by the area at the normal is equal to the radiance at an angle of theta. Okay, so the Lambertian material does not exhibit a change in radiance with changing cosine, right, or changing angle. Now, there is another way to think about Lambertian surfaces. If we were looking at, if we had a radiometer with a finite field of view, and we were looking at an element, some element of, the field of view of that radiometer was looking at the surface, a portion of a Lambertian surface. Okay, we could think of that Lambertian surface, that each point within my field of view is, each point within that field of view is reflecting light following the Lambert's cosine law. But with that finite field of view, as we rotate down, the area of the field of view, the ellipse actually starts to grow, because we would then have the ellipse would change according to 1 over the cosine of theta. And what ends up happening is, the ellipse gets bigger, but the number of points that we see in that field of view grows. And so in that case as well, this still holds true. I just wanted to point that out. That's used more in remote sensing applications. And so, the perfect Lambertian surface does not exist in nature. Many surfaces exhibit some form of somewhere between specular and diffuse reflectance. It's a mix. But the perfect Lambertian surface does not exist in nature. We can get pretty close with some engineered materials, but it still does not exist. And so if we think about now, what are some applications? What can we do with Lambertian materials? We can start with thinking, and not only what can we do with them, but then how can we characterize materials even more? And why I like to start here is because we end up having to use Lambertian materials in order to characterize materials, right? So we could we could start material characterization just by looking at the transmittance, reflectance, and absorbance relationships as light interacts with a material. And as I stated just momentarily ago, real materials exhibit some form of scattering, right? And so Lambertian materials are, or near Lambertian materials are reflecting light in this hemispherical pattern and following the cosine law for their intensity. But most materials are falling somewhere in between there. So what happens is we can't just measure the reflected light, right? We need to make sure when we are measuring a material, we are collecting all of the light that is reflecting off of the surface if we want to accurately understand the transmittance, reflectance, and absorbance, or precisely understand the transmittance, reflectance, and absorptance of that material. And so how do we measure materials that scatter? Well, we have to use an integrating sphere, right? So if, this is actually another good demonstration of a, diffuse reflector. The radiation angle comes in, light interacts with the surface, it reflects in this hemispherical distribution. In order to collect all of that, the light off of this surface, we need to use an integrating sphere. Or some form of collection chamber that allows us to collect all the light. And most commonly, an integrating sphere is used. Integrating spheres are interesting because, again, just like the perfect Lambertian surface, a perfect integrating sphere does not exist. A perfect integrating sphere would have a perfectly enclosed sphere and a perfect Lambertian surface on the inside. And then theoretically, what happens is the energy at any point, or the radiance at any point on the wall of the sphere, is equal. And so it is integrating the energy across the surface area of that sphere. And so, at LabSphere, we build integrating spheres, and we use our Lambertian surfaces to coat or line the inside of an integrating sphere. But of course, we have to put ports on them because otherwise they're not really useful for most applications. So again, in order to start measuring these materials for something like 8-degree hemispherical reflection, we need to use an integrating sphere that is also using a near Lambertian surface. And so today I'm just going to talk kind of at a high level about these. Again, I will be hosting a follow-up webinar in March that we will go into more details about reflectance measurements or spectroscopy applications using Lambertian surfaces and integrating spheres. We'll cover more topics then, including single beam, dual beam type measurement systems. But for now, just kind of going over the kind of the fundamentals. In this case, we're going to be measuring the reflectance of some sample in an integrating sphere with a single port. And that's possible. What we do is we put our reference material on the surface. That reference material needs to have a diffuse surface, and we would swap out that reference material with the sample. Okay, so we make a reference measurement and then we make a sample measurement. And then what we have to do when we're doing substitution is we have to kind of compensate for the throughput change that takes place due to swapping out the sample with the reference. Now, I think this is a really important point, is that, you know, a, a slight change in the reflectance of a material in a system, right? So a slight change in the total reflectance or of a material in a system that is doing some form of integrating of electromagnetic ratio, electromagnetic energy, is really critical, because what it does is it changes the throughput of that system. And so, sometimes people match their reference material to the sample. So, if you're measuring samples around 50%, you can use 50% characterization or something like that. Most often people are using 99% materials as their reference, but sometimes it's kind of like a matrix match in certain chemistry applications. That's one way to do it, but there's a more accurate way to do it, that would be using a comparison measurement where both the sample and the reference are always mounted to the sphere during the measurement process. And you have one entrance port for your incident light, and then you would swap out the reference with the sample to make your final measurement. So those are kind of two basic ways of doing a reflectance measurement. Again, having a diffuse reflectance surface as your reference is critical. And then if the integrating sphere is also using a diffuse reflectant surface. Similarly, we can do, there's a similar process for making transmittance measurements. With transmittance, we're measuring how much light transmits through a material, and most often that light is scattering through the material and needs to be collected in some form of hemispherical nature. So in reflectance measurements are often being conducted at an 8-degree incidence angle. So the light is it's coming in at an 8-degree angle. Transmittance can be done most transmittance that I've worked in is coming in at 0 degrees hemispherical. So the incident light is just coming in at a normal angle, and then you collect the light in the integrating sphere. And then calibration is just against an open port or 100% transmittance, right? This is often done, it's done on many materials. I've used this method a lot with sunscreen analysis, looking at the UVA protection factors and the UVA, UVB transmittance through different sunscreens. Now, again, you can also do this with a dual sphere type, dual port type system, where the sample is just moved from one port to the other. And the advantage, again, is maintaining some sort of, you're keeping your pulse on the throughput of that system as it changes. Because again, a throughput change can have a major effect on the system as a whole. And, just to think about that, if you have a material that is at 99% diffuse reflectance, right, and you go down to a material that is 98%, right, it's only a 1% change in overall reflectance. But if your ray of light bounces through that system 32 to 36 times, every time that ray of light interacts with the material, you get a loss of light. And so it adds up quite quickly. So some of the key applications that we see at LabSphere for material characterization uses, where people are using, integrating spheres, integrating chambers, and diffuse reflectance calibration standards, reference reflectance standards, are, in spectrophotometry, and that's generally in the UV vis near IR, with food quality assurance, quality control, and agriculture, pharmaceuticals, forensic, drug ID, and materials characterization in general. And then, of course, colorimetry, where people are looking at the, tri-stimulus values of different materials, for whether it be for food packaging, food quality assurance, quality control, paints, textiles, gemology, any place where understanding color is critical. And then certainly we see it in medical devices as well. People using standards for some sort of quick reference for surgical instrumentation and endoscopes and the like. Medical diagnostics, I was referencing before I've seen, while the integrating sphere has the best, it's very easy to characterize and understand how an integrating sphere is performing. But I've seen some customers who are using things like integrating sausages, I call them, and they're almost these like U-shaped integrating chambers that are used for creating uniform fields or collecting light in different diagnostic type systems. So another key application for diffuse materials is LiDAR. And in this case, we would be using a grayscale Lambertian reference reflectance target at some distance on a range. Okay, and we know basically we know how much we're measuring how much power is being received at the signal. We know the power of the laser source being used to create that signal. We would know the reflectance factor of the grayscale target being used for this measurement. We would know the effective collection area of our sensor. And, we would have a good idea, if not perfectly known, of the the optical transmission. We would probably really know, we would know our optical transmission in our system quite well. And then this is a bit of a variable through the atmosphere. But if we know all of that, what we can do is we can rearrange this equation and solve for R, and then we can start to understand the range sensitivity of our system. All right. And what the key wavelengths that are typically used in LiDAR are 850, 905, and 1550. There are different wavelengths that are used, but these are the key ones. And so, it's critical that the target be well characterized at your wavelength of interest. And of course, you don't just want to understand the range at 94% reflectance. So the most widely used reflectance levels for LiDAR range analysis are 10%, 50%, and 80% reflectance. And that makes sense if you think about what you see when you walk around outdoors. Rarely, unless it's winter, do you see things that are, above 90% reflectance. Even concrete is typically around 80. Certainly there are white paints and things that are greater than 80, but, the most of what we observe is somewhere in this region. And it's the same for an ADAS system as well. And so there are other tests that can be conducted with diffuse targets on LiDAR systems. So range we talked about, but you can also look at resolution by looking at, checkerboard type targets where you have different reflectance levels next to each other. It can help with false positive detection, spatial error, and a few more. And, in addition to just being used as a range tool, these targets can be essentially miniaturized, if you will, down to something like 1 inch and actually be used on board with the sensor. So you can kind of get some real time while it's in use. Understanding of how everything is performing, right? Or at least how critical your light source is behaving, right? So you can add the target into the optical system someplace out of view of the detectors, and kind of get and monitor what the signal is off of a smaller diffuse reflectance surface during operation. So related to LiDAR, but different, is time of flight characterization, right? So with time of flight, we would be using different wavelengths of interest. But again, these grayscale Lambertian reference reflectance targets are critical to understanding the performance of a time of flight system or sensor, and you can really start to understand how well things are detecting, what's the limits, what's the dynamic range, uh, um, and the like. So time of flight is also another key application where diffuse near Lambertian surfaces are critical. And so targets can be oh, just 1 second, please. Hey, sorry, I've recycled some of these slides, and there's audio that pops up on my end that you can't hear, and it always throws me off. So I apologize for not catching that before. Um, in the talk before, I actually ended up muting my computer, and then I just talked over Maria the whole time at the end because I thought something was wrong. So sorry about that. But yeah, so anyways, we see a lot of different application specific targets, right? Where, people want to understand how light behaves off of a curved surface. And so, like at LabSphere, we can coat many different things with our materials. And so we've coated, this is a 1 meter ball that we coated with a permaflex coating. And slanted surfaces, what people are looking for is how their time of flight, their LiDAR systems are behaving when they come in contact with these varied surfaces. And then again, I talked about the resolution. You can this is a good example of a checkerboard target, or a zebra stripe target as well, to help kind of resolve what's happening at this interface here. These targets are often quite large, meaning they're greater than a meter. The reason why they're so large is because they're put at a significant distance away from the sensor that is being tested, or the system that is being tested. And so you need to account for the spread in the point cloud in order to accommodate the measurement during that process. And so, another, this is not really application specific, but you know, because these are just optical components that are used in a variety of different systems, whether that be laser pump chambers, or laser cavities, to different types of lamp housings that are used in spectrophotometers or reflectometers, different types of baffles used in optical systems that require diffuse reflectance. Again, like housings with fiber optic ports and things like that. So basically for any application that may require diffuse light for either collection or reflectance, these materials can be manufactured in a way to enable the success of that optical system. Certainly there are limitations, but I always get kind of surprised at some of the applications that I've seen come through. This here is a 1 inch. It's about approximately 1 inch, or 25.4 millimeter spectralon ball, and it's really unique. I don't really know the exact application this is being used for. I'm assuming it's some sort of calibration technology or calibration method that someone needed to implement on a smaller surface. Uh, but that's unique. I actually come from a photoluminescence background in and and geology background. And my first job out of graduate school was at a gemological institute, and we actually used custom custom uh, color doped spectralon material. So it was doped with pigments in the yellow to actually and cut in the form of a gemstone in order to uh, validate colorimeter systems for the tri-stimulus values. So there's so many applications actually that these materials can be used in. We're only really limited by our imagination and of course the optical efficiency of the system we need to use them in. And again, so just kind of touching quickly on the materials LabSphere offers, we have Spectralon diffuse reflectance material. This is machinable and customizable material. Again, all of the optical components that we showed on the last page are made from Spectralon. The 99% Spectralon gives the highest diffuse reflectance of any known material on Earth, and that's over 99% across much of the vis and near IR. We can dope it with different pigments to give grayscale materials for linearity or dynamic range. It can be doped with rare earth elements for wavelength cals, and of course colors for different colorimetric applications. You can see here, this is a cosine plot of the intensity. The ideal would be the black line. I know this is hard to see, it's just an image, but you can see how well Spectralon responds to the varying angles. Like how this is such a near Lambertian material. It's great. And again, it's spectrally flat through basically from 350 to 2500 nanometers. There's some structure in some of the grayscale, but that's because of the pigment being used to dope it. Permaflect is, a highly durable coating. Again, this can be deployed outdoors. These go on large targets, but also small targets as well. If somebody's building a piece of equipment that needs to be used in a warehouse, sometimes they choose to coat it in something like Permaflect because Permaflect is easy. It's so easy to clean Permaflect and maintain that reflectance value. It does have a little bit of it's limited spectrally compared to Spectralon, but it's an application specific coating. So really, people are often using it from about 350 out to 1100 or beyond. But as you can see, when you get out here in the near and SWIR, you do get some absorbance taking place. And then this shows the cosine response at varying degrees, and so it's not as good as Spectralon, but it's quite good. And then the coating most people are familiar with is Spectraflect. That's just your standard barium sulfate type coating, and it gives a great diffuse reflectance of greater than 98% through 400 to 1100 nanometers. And the coatings, again, so Spectralon is a material that can be machined, and there are limitations to it. It expands and contracts. It has mechanical limitations, but it can be machined to accommodate many different applications. And then both Permaflect and Spectraflect can be coated onto machined surfaces. So, again, I didn't go around looking for different components that were coated yesterday. This is just showing kind of a basic integrating sphere, but really the it can be coated on many different surfaces and materials, and is really, again, only limited by the imagination and the actual mathematics of an optical system, and what the goal is that you're trying to accomplish. And so that's really it. This is just showing the spectral reflectance, 8-degree hemispherical reflectance for Spectraflect. But that's all I have today. So I just want to thank you again for joining us. And yeah, that's it. Thank you.
If anybody has any questions at this time, you can write it into the Q&A box, or you can raise your hand and I will unmute your line and you can ask your question directly to Lauren.
I've gone ahead and added my email to the chat. If anybody wants to ask questions offline as well, you can always feel free to email me.
As a reminder, this presentation is being recorded and the recording will be available shortly after the end of the session.
Okay, so we did get a question about LabSphere manufacturing diffuse reflectance materials for infrared wavelengths. And so we do make a diffuse reflectance material. Just out of curiosity, is there a specific wavelength that you're interested in that you can share, or is it, I mean, is it beyond 2500 nanometers? Roughly 1 to 20. Yeah, so we do have infragold, which is a diffuse reflectance material. It exhibits about 95 to 94 to 95% diffuse reflectance. You know, beyond 1 micron really, and pretty consistent out to where you're interested in 20 microns. The BRDF has, you know, it's in infragold, right? So there's definitely going to be some specular components. So the BRDF isn't as good as you know, something like Spectralon or Permaflex, but it is, you know, it is diffuse reflectance. I can send you this is Mike M. We do have a materials guide that does cover, infragold is included in that, and there's a section on it that shows its BRDF and some other properties. So I can send that along to you and you can review the material there. That would be helpful, probably.
I'm looking, I don't see any other questions or hands raised.
All right, you're welcome, Mike. Yeah, so, okay, if there are no more, oh, there's one came in on the Q&A.
Do
Can
you
you show
see
me
that?
how to the solid angle of the sphere output? Yes, I'd radiometric and photometric quantities. Okay, so, you know, I can't show you how to do that right now. However, so the question is just, I don't know if everybody can see this or not. Can you show me how to calculate the solid angle at the sphere output port? So yes, we do have some documentation on that, that again, I can send along. We have uh, you know, a radiometry and photometry guide that goes into these details a lot more. So that's coming in from Lintron. I will send that over to you as well. Okay, so I'll make sure you get a copy of that, and then you know, you can ask us additional questions, and we'll be happy to answer them.
And our next webinar in the series will be held on February 12th. And we have sessions at 9 a.m. and 3 p.m. again. You can locate those links on our website to register for those webinars, but we'll probably be sending out emails for those anyway.
All right, perfect. Thank you, everyone.
Thank you.
Go ahead.
Thank you. That's it. Bye, everybody.